The dawn of Fabless, a paradigm shift. The Silicon Schism. The history of the modern world is written in silicon, but the authorship of that history underwent a radical and violent revision in the late 20th century. For the first 30 years of the semiconductor industry's existence, the prevailing dogma was one of monolithic unity. To design a chip was to manufacture it. This structure, known as the Integrated Device Manufacturer model, was not merely a business strategy, it was an industrial religion. It posited that the intricate dance between the microscopic architecture of a transistor and the physical alchemy required to print it on a wafer were so complex that the two functions could never be separated. Giants like Intel, Texas Instruments, and NEC dominated the landscape, their towering vertical integration serving as both a fortress against competition and, eventually, a prison for innovation. The dawn of the Fabless model, a bifurcated industrial structure where design and manufacturing are decoupled, was not an inevitable evolution, but a forced disruption. It was born from the collision of unforgiving economic laws and the singular vision of an exile from the American corporate establishment, Morris Chang. When Taiwan Semiconductor Manufacturing Company, TSMC, was founded in 1987, it was widely ridiculed as a solution looking for a problem. Critics argued that without its own products, a pure-play foundry would be relegated to the scraps of the industry, forever subsisting on the low-margin overflow of the true titans. Instead, the creation of the dedicated foundry unleashed a Cambrian explosion of technological creativity. By removing the prohibitive capital barrier of building a fabrication plant, or fab, TSMC democratized access to the bleeding edge of physics. This review provides an exhaustive analysis of this paradigm shift. It dissects the economic pincers of Moore's Law and Rock's Law that rendered the IDM model unsustainable for the middle class of the industry. It chronicles the granular history of Morris Chang's radical vision, moving from his rejected proposals at Texas Instruments to the greenfield struggles in Hsinchu. Finally, it details the arduous decade-long process of building trust in an industry defined by paranoia, illustrating how a commitment to integrity and the Chinese wall allowed fierce competitors like NVIDIA and ATI to coexist within the same cleanroom, fundamentally rewriting the geopolitical and economic map of the 21st century. The pre-TSMC era, the fortress of vertical integration. To understand the magnitude of the fabless revolution, one must first appreciate the rigidity of the regime it displaced. In the 1970s and 1980s, the semiconductor industry was the domain of the IDM. Companies such as Intel, Motorola, Texas Instruments, TI, Toshiba, and Hitachi controlled every link in the value chain. They designed the instruction sets, they developed the process recipes, they built the factories, they packaged the chips, and they sold them to end users. This integration was rooted in technical necessity. In the early days of large-scale integration, LSI, the interaction between circuit design and process manufacturing was fluid and undefined. A design engineer might need a specific doping profile to achieve a target switching speed, requiring the process engineer to alter the furnace temperature or diffusion time. This tight coupling meant that innovation was iterative and internal. Real men have fabs, the famous declaration attributed to AMD founder Jerry Sanders, was not just bravado, it was an economic statement of fact. Without a fab, a designer was an artist without a canvas, dependent on the charity of competitors to bring their ideas to physical reality. The IDM model offered immense power. It allowed companies to optimize yields for specific high-volume products, such as dynamic random access memory, DRAM, or microprocessors. However, this strength concealed a fatal structural flaw. It required massive, continuous capital investment that only the largest entities could sustain. As the industry moved from the era of thousands of transistors per chip to millions, the cost of entry began to rise exponentially, creating a rich-get-richer dynamic that stifled independent innovation. Two relentless economic forces converged in the 1980s to destabilize the IDM model: Moore's Law and Rock's Law. While Moore's Law is universally celebrated as the engine of digital progress, predicting the doubling of transistor density every 18 to 24 months, Rock's Law is its darker, predatory twin. Named after venture capitalist Arthur Rock, it posits that the cost of a semiconductor fabrication plant doubles every 4 years. In 1983, constructing a state-of-the-art semiconductor fab was a manageable corporate expense, costing approximately $50 million. This was a significant sum, but within the reach of mid-sized electronics firms. However, as the industry pushed towards submicron geometries, the physics of lithography and etching became exponentially more difficult and expensive. By the late 1980s, the cost of a leading-edge facility had ballooned to hundreds of millions of dollars. By the mid-1990s, it would breach the $1 billion mark. This capital escalation created a gambler's ruin scenario for mid-tier IDMs. To stay competitive, a company had to commit extraordinary sums to develop the next process node years before demand was certain and before yields were proven. If a company missed one single product cycle, as Intel famously did with memory in the mid-80s, or as countless others did during the DRAM wars, the amortization costs of the idle fab could bankrupt the firm. This dynamic forced a brutal consolidation. Innovation was no longer limited by human creativity, but by the balance sheet. A brilliant engineer with a revolutionary architecture for a graphics processor or a network switch had no path to market. They could not raise $200 million to build a fab, and existing IDMs had no incentive to manufacture chips that might cannibalize their own product lines. The industry was effectively strangling its own future. Before the dedicated foundry, the few proto-fabless companies that existed lived a precarious existence. Firms like LSI Logic and VLSI Technology, founded in the early 1980s, attempted to break the mold by focusing on application-specific integrated circuits, or ASICs. But these companies were often hybrids, owning some manufacturing capacity while outsourcing the rest, or acting as brokers between designers and IDMs. The outsourcing experience was fundamentally adversarial. A small design house typically had to approach a large IDM, often a direct competitor, and beg for excess capacity. This arrangement was fraught with conflict of interest. An IDM like Toshiba, Texas Instruments, or Motorola would use external orders to fill their lines during economic downturns. However, the moment the market cycle turned and demand for their own product spiked, the external customers were unceremoniously cut off. Worse, utilizing an IDM's fab meant handing over the crown jewels, the proprietary circuit designs or masks, to a rival. There was a persistent and justifiable paranoia that the IDM's engineers would reverse engineer the customer's IP, learn the secret sauce, and launch a competing product a year later. This capacity insecurity and IP anxiety meant that the fabless model could not scale. It remained a niche curiosity, incapable of challenging the dominance of the vertical giants. Morris Chang's radical vision: the deconstruction of value. The resolution to this industrial impasse came from an unlikely source, a 56-year-old executive who had effectively been put out to pasture by the American corporate system. Morris Chang's biography is essential to understanding the DNA of the foundry model. Born in Ningbo, China in 1931, Chang fled war and revolution, arriving in the United States at age 18. Educated at Harvard, MIT, and Stanford, he spent 25 years at Texas Instruments, rising to become the group vice president in charge of the company's entire global semiconductor business. At TI, Chang was not merely a manager, he was a manufacturing theorist. He pioneered the concept of pricing ahead of the cost curve. He understood that semiconductor manufacturing was a function of cumulative volume. Every doubling of cumulative volume led to a predictable decline in defect density and cost, yield improvement. Therefore, the strategic imperative was to sacrifice short-term profit to maximize volume, drive down the learning curve, and achieve a cost structure that competitors could not match. However, Chang's vision eventually outgrew TI. In 1976, he presented a prescient 16-page report to TI's Strategic Planning Committee. He argued that the cost of entry for manufacturing was becoming too high for non-specialized firms, and that TI should invest heavily to become a manufacturer for the external market, effectively a foundry. The proposal was radical, arguing for the decoupling of design and manufacturing. TI's leadership, entrenched in the IDM mindset and shifting focus to consumer electronics, calculators, and watches, shelved the report. It was a lost vision that would have changed history had TI adopted it. After being passed over for the CEO role at TI and a brief, culturally mismatched stint as president of General Instrument, Chang resigned in 1985. To the Silicon Valley elite, he was a respected but fading figure of the previous generation. It was then that the Taiwanese government, specifically the visionary minister K.T. Lee, recruited Chang to head the Industrial Technology Research Institute. Taiwan in 1985 was at a crossroads. It had a robust assembly economy but lagged in high technology. It had no IDMs, no world-class design houses, and no marketing presence in the U.S. Chang assessed the island's strengths: a surplus of disciplined, highly educated engineers, a government willing to make long-term capital investments, and a lack of legacy baggage. Chang's genius was to invert Taiwan's weaknesses. Because Taiwan had no design capabilities, it had no products to protect. Therefore, it could promise prospective customers something no American or Japanese IDM could. It would never compete with them. This gave birth to the pure-play foundry concept. TSMC would not be a chip company. It would be a manufacturing service utility, a virtual fab for the rest of the world. The founding of TSMC in 1987 was a public-private experiment of unprecedented scale. The Taiwanese government provided 48.3% of the initial capital through the National Development Fund, but Chang insisted on a corporate structure that demanded profitability, rejecting the model of a state-owned enterprise. He knew that for TSMC to succeed, it needed technology transfer from a Western major to bridge the gap between ITRI's research capabilities and commercial mass production. Chang went on a roadshow to pitch the foundry concept to the titans of the industry. He approached Intel, trusting in his old connections. Intel's then executive, Craig Barrett, listened but declined, seeing no value in a dedicated foundry. He approached Japanese firms like Toshiba. They too declined. The industry consensus was that a foundry would only attract junk business, low-margin chips that weren't worth the IDM's time. The Philips breakthrough. The only company to say yes was the Dutch giant Philips. Philips agreed to invest $58 million for a 27.5% equity stake. More importantly, the deal included a crucial technology transfer agreement. Philips licensed its 2-micron and later 3.5-micron production technologies to TSMC and cross-licensed its patent portfolio. This partnership was the sine qua non of TSMC's survival. It provided legal air cover. The patent cross-licensing protected TSMC from immediate lawsuits by other IDMs. Technical baseline. It allowed TSMC to start production with a proven, albeit slightly trailing, process. Anchor customer. Philips used TSMC as an overflow valve, providing base load volume to keep the lines running. The remaining 25% of capital was raised from wealthy Taiwanese families, such as the owners of Formosa Plastics, who invested largely due to government pressure rather than conviction in the business model. The Crucible of Trust. Surviving the Green Field. 1987-1992. TSMC officially launched on February 21, 1987. Its first facility, Fab 1, was a leased line from ITRI in Hsinchu. The early years were, in Chang's own words, touch and go. The fabless industry did not yet exist in any meaningful size. TSMC had built a solution for a market that had not yet formed. For the first 4 years, 1987-1991, TSMC struggled to fill its capacity. Chang, despite his status as a former Group VP of TI, acted as the lead salesman. He faced a skeptical market. The prevailing view was that manufacturing process technology was the primary differentiator of chip performance. If a company didn't own the fab, how could it optimize the chip? TSMC was forced to take whatever orders it could get, often serving as a buffer for IDMs like Intel and Motorola, who needed temporary capacity for older, low-margin logic chips. The single greatest obstacle to TSMC's growth was the crown jewels problem. For a semiconductor design firm, the mask set, the blueprint of the chip, is the company's entire value. Handing this over to a third-party manufacturer in Asia, a region then associated with lax intellectual property enforcement and reverse engineering, was seen as an existential risk. Designers feared that a foundry might leak the design to a competitor, use the process knowledge to improve the yields of a rival, eventually enter the market with a competing product, the Samsung fear. To overcome this, Morris Chang elevated integrity to an operational doctrine. It became the first of TSMC's core values, ahead of innovation or commitment. This was not abstract moralizing, it was a commercial necessity. The Chinese Wall. TSMC implemented rigorous information security protocols known as Chinese walls. Engineering teams working on a chip for ATI were physically and digitally segregated from teams working on a chip for NVIDIA. Proprietary data was siloed. Most importantly, Chang codified the non-compete pledge. TSMC would never design a chip. It would never sell a product under its own brand. This pure play status created a misalignment of incentives that favored the customer. TSMC only succeeded if the customer succeeded. This contrasted sharply with IDMs like Samsung or Intel Foundry Services, where the manufacturing arm serves external clients who are often competitors to the parent company's product arm. While occurring slightly later in its history, early 2000s, TSMC's aggressive defense of IP against SMIC, Semiconductor Manufacturing International Corp., retroactively validated its early promises. When SMIC, founded by former TSMC executive Richard Chang, was suspected of poaching staff and stealing process recipes, the trade secrets, TSMC launched a relentless multi-year legal campaign in U.S. courts. The litigation revealed that SMIC had achieved process nodes like 0.18 micron with suspicious speed, mirroring TSMC's exact technical parameters. TSMC eventually won a massive settlement, including $200 million and an equity stake in SMIC. This scorched earth legal defense demonstrated to the global fabless community that TSMC viewed IP, both its own and its customers, as inviolable. It proved that the integrity value had teeth. The first believers, catalyzing the ecosystem. The foundry model could not succeed in a vacuum. It required a symbiotic partner, the fabless entrepreneur. In the late 1980s and early 1990s, a new generation of Silicon Valley startups emerged. These companies had brilliant architectural ideas but lacked the capital to build fabs. They were the first believers who bet their survival on Morris Chang's virtual fab. The field programmable gate array, FPGA industry, was the nursery of the fabless model. FPGAs are blank slate chips that can be reprogrammed by the customer. Because they are standard, high-volume parts that require advanced logic processes to maximize density, they were ideal drivers for TSMC's learning curve. Altera, founded in 1983, and Xilinx, founded in 1984, were fierce rivals. Initially, they scrambled for capacity at various IDMs like Seiko, Sharp, or Ricoh. However, as they moved to denser geometries, they needed a partner who would prioritize their technology roadmap. Altera formed a deep, strategic alliance with TSMC. This partnership went beyond a simple vendor-client relationship. Altera pushed TSMC to improve its defect densities, and in return, Altera provided the volume TSMC needed to fill its lines. This symbiosis culminated in 1996 with the formation of WaferTech, a joint venture between TSMC, Altera, Analog Devices, and ISSI, to build TSMC's first fab in the United States, Camas, Washington. This was a watershed moment. Fabless customers were now co-investing in the manufacturing infrastructure, blurring the lines between the two models while maintaining the separation of design and execution. If Altera validated the model, NVIDIA proved its explosive potential. The story of NVIDIA's relationship with TSMC is one of the great legends of the semiconductor industry, illustrating the personal nature of the trust Morris Chang cultivated. In 1997, NVIDIA was a 4-year-old startup teetering on the brink of bankruptcy. Its first chip, the NV1, had been a commercial failure due to its reliance on quadratic texture mapping, a non-standard technology. And Jensen Huang, the NVIDIA co-founder and CEO, knew the company had one last shot, the RIVA 128. This chip would use standard polygons and required a leading-edge process to achieve the necessary performance to compete with 3DFX. NVIDIA, however, was cash poor and lacked the manufacturing relationships of established players. Huang wrote a cold letter to Morris Chang. In the letter, he admitted NVIDIA was small, but claimed it had a design that would consume massive capacity if successful. He sent it to TSMC's Hsinchu headquarters. Chang, who typically dealt with titans like Intel or Motorola, was intrigued by the audacity of the note. He called Huang. The story goes that Huang picked up the phone in a noisy open-plan office where his engineers were arguing. Hearing Morris Chang's voice, Huang yelled, "Quiet! Morris Chang is calling me." In that call and subsequent meeting, Chang agreed to manufacture the RIVA 128. He bet on the man and the architecture, not the balance sheet. It was a masterstroke. The RIVA 128 was a hit, saving NVIDIA. The subsequent GeForce 256 defined the modern GPU. NVIDIA grew to become one of TSMC's top 5 customers within 3 years. By taking a risk on a fabless startup, TSMC secured a partner that would, decades later, drive the AI revolution and become the most valuable semiconductor company in the world. Qualcomm, founded in 1985, presented a different challenge. Focused on CDMA wireless technology, Qualcomm dealt with mixed-signal chips, combining analog radio signals with digital logic. This required specialized process technologies. Qualcomm realized early on that owning a fab to produce such complex, rapidly evolving chips would be a capital sinkhole. By outsourcing to TSMC, Qualcomm could focus entirely on the complex mathematics of wireless transmission and the integration of the system on chip. TSMC, in turn, developed specific mixed signal and RF radio frequency process nodes to accommodate Qualcomm. This partnership allowed Qualcomm to dominate the 3G and 4G eras, scaling production to hundreds of millions of units without ever pouring concrete for a factory. Scaling the model, the mechanics of catch-up. In its first decade, TSMC did not attempt to lead the world in transistor physics. It adopted a pragmatic N-1 strategy. It offered process technologies that were one generation, node, behind the leading IDMs like Intel and NEC. If Intel was manufacturing at 0.8 micron, TSMC would offer a robust, high-yield 1.0 micron process. This strategy served two purposes. Risk mitigation. It allowed TSMC to use depreciated equipment types and proven process recipes, keeping costs lower. Market fit. Most fabless companies making controllers, consumer electronics, or low-end comms chips did not need the bleeding edge. They needed reliability and cost-effectiveness. However, Chang knew N-1 was a temporary station, not a destination. He used the profits and the massive volume of data generated by processing wafers for hundreds of different customers to accelerate R&D. TSMC's unique advantage was wafer diversity. An IDM might run 10 products through its fab. TSMC ran thousands. This gave TSMC's yield engineers a statistically superior dataset to identify defects and optimize the process. By the late 1990s, TSMC reached parity with the IDMs. By the 2000s, it was competing for the lead. To further lock in the fabless industry, TSMC worked to lower the transaction costs of design. In the IDM world, design tools were proprietary. TSMC championed the open ecosystem. It developed standardized process design kits, or PDKs, files that described the electrical and physical rules of the fab to the designer software. This allowed electronic design automation companies like Cadence and Synopsys to build tools that worked seamlessly with TSMC. Furthermore, TSMC encouraged the growth of third-party IP providers like ARM and design service firms like Global Unichip Corp or UGC. This meant a startup didn't need to design a USB controller or a memory interface from scratch. They could license it, use TSMC's PDK to integrate it, and send the file to the fab. This Lego block approach reduced the time to market for a new chip from years to months, fueling the dot-com boom's hardware explosion. The new economics. Why the IDMs fell. As the 2000s progressed, Rock's Law continued its relentless march. The cost of 300mm wafer fabs and the transition to copper interconnects pushed fab costs over $3 billion. The IDMs faced a crisis of utilization. To justify a $3 billion fab, a company needed massive, consistent revenue. If a product cycle failed, the depreciation costs would destroy the company's margins. TSMC, by aggregating the demand of the entire fabless market, smoothed out these variances. If the PC market slumped, the mobile market might rise. If NVIDIA had a bad quarter, Qualcomm might have a good one. This portfolio effect gave TSMC a more stable utilization rate than any single IDM. Intel, the mightiest IDM, fell victim to its own success. For years, it treated foundries as sources of low-end capacity. It failed to see that by funding the foundry ecosystem, it was enabling its future competitors. By the time mobile computing arrived, the iPhone, the fabless foundry ecosystem, ARM plus TSMC, moved faster than the monolithic IDM, Intel x86. Apple could iterate its A-series chips every year utilizing TSMC's latest node, while Intel was bogged down by its internal yield struggles and the need to feed its massive x86 legacy manufacturing base. The legacy of 1987. The founding of TSMC in 1987 was the geopolitical and industrial equivalent of the splitting of the atom. Before TSMC, the power to create silicon was bound to the power to design it. By shattering this bond, Morris Chang released a tremendous amount of energy, the creative potential of thousands of designers who no longer needed $1 billion to change the world. The shift was total. Today, the world's most valuable semiconductor companies, NVIDIA, Broadcom, AMD, Qualcomm, own 0 factories. They are pure manifestations of human intellect, etched into silicon by the virtual fab that Chang envisioned. The dawn of Fabless was not just a business model innovation, it was a survival strategy that became a dominant strategy. It leveraged the brutal economics of Rock's law against the incumbents, turning the heavy burden of manufacturing into a service utility. It required navigating the minefield of IP paranoia through a sheer force of corporate character and integrity. As we stand in the era of 3nm chips and angstrom-level innovation, where a single fab costs $20 billion, the logic of 1987 stands vindicated. No single company, not even the mighty Apple or NVIDIA, can bear the weight of the physical world alone. They all stand on the shoulders of the foundry model, the industrial platform that quietly, invisibly, and relentlessly powers the digital age. The infrastructure of democratization, OIP, and the ecosystem. To understand how a small startup in Silicon Valley or a system integrator in Shenzhen could design a chip rivaling Intel's, one must first understand the infrastructure that made it possible. The foundry model of the 1990s was transactional. Send us the GDSII file and we will send you wafers. The foundry model of the 2000s, pioneered by TSMC, became collaborative. As process nodes shrank to 65 nanometers and 40 nanometers in the mid-2000s, the interaction between design layout and manufacturing yield became critical. Design for manufacturing, DFM, was no longer a nice-to-have, it was a survival requirement. In an IDM, the design team sits down the hall from the process engineers. If a layout structure causes a lithography defect, they talk and fix it. In the fabless foundry model, this feedback loop was broken. The throw-it-over-the-wall approach was failing, resulting in costly respins and delayed time to market. TSMC's response in 2008 was the Open Innovation Platform, OIP. This was not merely a marketing initiative, but a fundamental restructuring of the supply chain's digital nervous system. OIP unified the disparate elements of chip creation, EDA tools, IP blocks, and process technology under a single interoperable standard. A cornerstone of the OIP was the Active Accuracy Assurance Initiative. Before OIP, a fabless designer had to guess whether a specific tool from Synopsys or Cadence would perfectly interpret the design rules of a specific TSMC node. Discrepancies could lead to silicon failure. Under AAA, TSMC began certifying EDA tools and IP libraries against its own internal golden models. Significance. This meant that TSMC guaranteed the accuracy of the tools. A startup could purchase a certified tool chain and trust that the digital twin of their chip in the software would match the physical atoms on the wafer in Taiwan. Reduction of risk. This dramatically de-risked the design process. For a venture-backed startup, removing the foundry compatibility risk was equivalent to lowering the barrier to entry by millions of dollars. Perhaps the most profound democratizing force was the IP alliance. Modern systems on chips, SoCs, are incredibly complex, containing CPUs, GPUs, memory controllers, DDR, high-speed interfaces, PCIe, USB, and connectivity radios, Wi-Fi, Bluetooth. Designing all of these from scratch is impossible for a small team. The OIP catalog aggregated tens of thousands of silicon-proven IP titles, growing to over 70,000 by 2023. The startup advantage: a company like Ambic Micro or Credo Technology did not need to hire 50 engineers to build a standard USB controller. They could license a verified block from the IP Alliance, drop it into their design, and focus 100% of their R&D resources on their differentiating secret sauce, such as sub-threshold voltage logic or high-speed SerDes. This modular approach reduced design cycles by 6 to 12 months. In the fast-paced consumer electronics market, this speed was often the difference between life and death. Extending beyond the OIP, TSMC formalized the Grand Alliance, a broader coalition including equipment suppliers like ASML and Applied Materials, and materials vendors. This alliance created a synchronized roadmap. When TSMC planned to introduce a new node, such as 16-nanometer FinFET, it coordinated years in advance with the entire supply chain. For the Fabless ecosystem, this meant that on the day a new process node was available, the entire supporting infrastructure, the lithography machines, the photoresists, the EDA tools, the IP blocks, was ready to go. This synchronization allowed fabless companies to compete directly with Intel on process technology leadership, a feat previously thought impossible for disaggregated entities. The value chain aggregators, bridging the scale gap. While the OIP provided the technical tools, the commercial logistics of working with the world's largest foundry remained a significant hurdle for small players. TSMC is built for scale. Its gigafabs churn out hundreds of thousands of wafers per month. Engaging directly with TSMC typically requires substantial volume commitments and creditworthiness that an early-stage startup simply does not possess. To solve this scale gap, TSMC empowered a tier of partners known as value chain aggregators, or VCAs. These companies act as the commercial and technical bridge between the long tail of innovation and the massive industrial machine of TSMC. VCAs are independent design service companies that aggregate demand from multiple small customers to meet TSMC's volume thresholds. They provide a turnkey service. A startup approaches them with an idea or a net list, and the VCA handles the physical layout, mask generation, wafer ordering, packaging, and testing. Global Unichip Corp. GUC. As a TSMC subsidiary, GUC is deeply integrated into the TSMC ecosystem. It allows startups to access the most advanced nodes, including 5 nanometers and 3 nanometers, without needing their own operations team. GUC manages the entire supply chain, effectively giving a 10-person startup the operational capabilities of a Fortune 500 company. All-Chip Technologies. Specializing in high-performance computing, HPC, All-Chip has been instrumental for companies in the cryptocurrency and AI sectors. All-Chip's expertise in complex physical design allows them to help startups tape out massive, power-hungry chips that push the limits of the process capability. Avnet ASIC. This VCA focuses on a broader range of applications, including industrial and automotive. By partnering with Avnet, companies can access mature and mainstream nodes for products that don't require the bleeding edge but do require extreme reliability. The VCA program enabled a wave of specialized silicon that would never have been economically viable under the old IDM model. MOS chip and Synapse design. These DCA-VCA partners help fabless companies in regions like India and Silicon Valley implement designs. For instance, MOS chip helps customers with RTL to silicon implementation, allowing domain experts in fields like medical diagnostics or industrial automation to build custom chips without needing deep silicon expertise. Ensilica, a UK-based VCA that helps companies in the automotive and industrial sectors. They recently joined the OIP DCA to help bring mixed-signal ASICs to market, proving that the democratization extends beyond digital logic to complex analog domains. A critical tool in the VCA arsenal is the multi-project wafer, often called a shuttle run. The cost of a full mask set for a modern node is staggering, ranging from $50 million for 28 nanometers to over $500 million for 3 nanometers. For a startup, risking this capital on a first design is impossible. The mechanism. The MPW shuttle aggregates designs from dozens of different customers onto a single mask set. Instead of paying for the whole mask, a startup pays for a seat on the shuttle, costing perhaps $50,000 to $500,000, depending on the area and node. This allows for iterative failure. Startups like Sentient or Mythic could prototype their novel AI architectures, test them in silicon, and refine them before committing to the massive expense of a full production mask set. This mechanism effectively subsidized risk-taking in hardware, fueling the renaissance of semiconductor startups in the late 2010s. The mobile revolution, 28 nanometers to info packaging, 2010 to 2020. The post-PC era was defined by the smartphone. While the desktop era was dominated by the Wintel duopoly, the mobile era was a chaotic, vibrant ecosystem of ARM-based innovation. TSMC was the engine room of this transformation, providing the silicon that powered everything from the cheapest $50 Android phone to the premium iPhone. While TechPress focuses on the bleeding edge, the 28-nanometer node, introduced by TSMC in 2011, was arguably the most democratizing technology of the decade. Technical sweet spot. 28 nanometers was the last planar transistor node before the industry switched to the more complex and expensive FinFET architecture. It utilized high-K metal gate, HKMG technology, to reduce leakage, offering a massive performance leap over 40 nanometers. Broad portfolio. TSMC broke from tradition by offering a wide menu of 28-nanometer flavors, 28 HP, high performance for tablets, 28 HPM-M, mobile for smartphones, 28 HPC and HPC Plus, cost optimized, and 28 ULP, ultra-low power for IoT. This flexibility allowed chipset vendors like MediaTek and Qualcomm to flood the market with affordable, powerful system-on-chips, or SoCs. This silicon enabled the rise of Chinese OEMs, Xiaomi, Oppo, and Vivo, and brought smartphones to billions of people in emerging markets. The longevity of the 28-nanometer node also provided a stable platform for IoT startups who could rely on mature, high-yield manufacturing for years. The shift of Apple's A-series chips from Samsung to TSMC is the defining partnership of the mobile era. In the early years of the iPhone, Apple relied on Samsung for its manufacturing. However, as the legal and competitive war between the two giants heated up, Apple sought a new partner. The transition. The pivot began with the A8 chip, iPhone 6, on TSMC's 20nm node in 2014. But the decisive moment came with the A10 Fusion chip for the iPhone 7 in 2016. The chipgate context. In the previous generation, A9, for iPhone 6s, Apple had dual-sourced from Samsung and TSMC. Users and reviewers discovered that the TSMC-manufactured chips ran cooler and offered better battery life, despite the nominal node disadvantage. This real-world validation proved TSMC's superior yield and process control. TSMC secured exclusivity for the A10, not just through transistor performance, but through a radical innovation in packaging, integrated fan-out, or INFO. The problem. Traditional mobile chips used package-on-package technology, where the DRAM memory was stacked on top of the processor using a substrate or a mini circuit board. This substrate added thickness and limited thermal dissipation. The INFO solution. TSMC's INFO technology eliminated the substrate entirely. It used a redistribution layer, or RDL, to fan out connections directly from the silicon die. This resulted in a package that was significantly thinner, allowing for slimmer iPhones or larger batteries, and had superior electrical and thermal properties. Democratization of advanced packaging. Initially exclusive to Apple, INFO technology eventually trickled down to other customers like MediaTek and Qualcomm, allowing the broader Android ecosystem to close the form factor gap with Apple. This move marked TSMC's transition from a chip maker to a system integrator, a capability that would become crucial in the AI era. Stress testing the ecosystem. The crypto boom 2017 to 2018. Before the current AI supercycle, the semiconductor industry faced a different kind of tidal wave, the cryptocurrency mining boom. This period, often dismissed as a speculative bubble, was in fact a critical stress test for the Fabless foundry model. It demonstrated TSMC's ability to support non-traditional startups scaling at unprecedented velocity. Bitmain, a Beijing-based startup founded in 2013, became the dominant force in Bitcoin mining hardware. By designing application-specific integrated circuits, ASICs, solely for the SHA-256 hashing algorithm, Bitmain achieved efficiencies orders of magnitude better than GPUs. Hyperscaling. In 2017, demand for Bitmain's Antminers exploded. The company went from a niche player to generating $2.5 billion in revenue in a single year. TSMC impact. Bitmain rapidly became one of TSMC's top 10 customers, contributing 3 to 5% of the foundry's total revenue, roughly equivalent to NVIDIA at the time. This was a shock to the industry. A 4-year-old startup was consuming as much advanced silicon as a 20-year-old graphics giant. The relationship with Bitmain and other crypto startups like Canaan Creative and eBang taught TSMC valuable lessons that would later apply to AI. Speed. Crypto miners needed the absolute latest node to maintain hash rate competitiveness. Bitmain moved aggressively from 16 nm to 7 nm, pushing TSMC to ramp yield faster than conservative automotive or industrial customers would require. Power density. Mining chips run at 100% utilization, 24/7, generating immense heat. Reliability data from millions of these chips operating in harsh environments helped TSMC refine its transistor profiles for high-current, always-on workloads. exactly the profile of a modern AI training cluster. Financial resilience. The crypto bust in 2018, where mining demand evaporated overnight, taught TSMC how to structure contracts and prepayments to protect against volatile, hot commodities. This experience influenced the strict allocation policies seen today in the AI chip shortage. The hyperscaler revolt, taking control of silicon. One of the most profound shifts of the post-2015 era is the entry of cloud giants, hyperscalers, into the world of chip design. Realizing that general-purpose silicon from Intel could not meet their specific efficiency and scale requirements, companies like Google, Amazon, and Tesla leveraged the TSMC ecosystem to become fabless semiconductor companies in their own right. Google began its custom silicon journey in 2015 with the TPU V1, designed to accelerate internal machine learning workloads for search and photos. Evolution. The TPU program has evolved through multiple generations, moving from 28 nm to 16 nm, 7 nm, and 5 nm. Google partnered with Broadcom and MediaTek for ASIC design services, but relied on TSMC for the critical manufacturing. Strategic shift. Recent reports indicate that for the Tensor G5 and future server TPUs, Google is deepening its direct relationship with TSMC, utilizing the 3 nm node and info packaging. This marks a move away from Samsung, used for early mobile Tensor chips, and underscores TSMC's role as the gold standard for AI performance. Impact. By building the TPU, Google decoupled its AI roadmap from NVIDIA's product cycle, gaining a strategic cost and performance advantage in training its massive Gemini models. AWS leveraged its acquisition of Annapurna Labs to radically alter the data center economics. Graviton. AWS introduced the Graviton series of ARM-based CPUs, manufactured on TSMC's 7 nm and 5 nm nodes. These chips offered 40% better price performance than comparable x86 instances, forcing Intel and AMD to compete with their own biggest customer. AI silicon. AWS expanded into AI with Trainium, training, and Inferentia, inference chips. These are developed in partnership with Alchip and Marvell, using TSMC's advanced packaging to integrate high-speed memory. This custom silicon strategy allows AWS to offer differentiated AI cloud services that aren't solely dependent on GPU allocation. Tesla's journey exemplifies the vertical integration path. Initially relying on Mobileye and then NVIDIA, Tesla eventually designed its own full self-driving computer. Foundry agility. Tesla utilized both Samsung 14 nm and TSMC 7 nm and 5 nm for different generations of its FSD chips. The ability to switch foundries and access the best node for power performance area PPA allowed Tesla to deploy a supercomputer-class chip in a consumer vehicle, a feat impossible if they had to build their own fabs. The AI supercycle and the Cambrian explosion of hardware. The current era, dominated by generative AI and large language models, or LLMs, has triggered a Cambrian explosion of hardware startups. These companies are betting that the transformer architecture requires a new kind of computer, not just a better GPU. TSMC's ecosystem is the bedrock of this rebellion. Cerebras Systems presents perhaps the most audacious example of TSMC's enabling power. Standard chip manufacturing is limited by the reticle, the maximum area of light a lithography machine can project, roughly 858 square millimeters. The wafer scale engine. Cerebras wanted to build a chip the size of an entire 300mm wafer to eliminate the latency of moving data between separate chips. This was theoretically impossible with standard tools. The TSMC partnership. TSMC worked with Cerebras to develop a custom manufacturing flow that stitched the reticles together across the scribe lines, creating a single massive processor with trillions of transistors and hundreds of gigabytes of on-chip SRAM. This collaboration proved that TSMC was willing to bend the rules of physics and manufacturing for a startup with a radical idea, provided the engineering partnership was strong. UK-based GraphCore aimed to optimize AI compute with its Intelligence Processing Unit, or IPU, wafer-on-wafer. GraphCore utilized TSMC's 7nm process, but added a twist: wafer-on-wafer technology. They bonded a power delivery wafer directly to the logic wafer. This 3D stacking smoothed out power delivery, allowing the chip to run faster and cooler. SOIC pipeline. GraphCore served as a lead partner for TSMC's SOIC, System on Integrated Chips technology roadmap, showcasing how startups often serve as pipe cleaners for novel manufacturing techniques before they reach mass adoption by giants like Apple. Tenstorrent. Led by legendary chip architect Jim Keller, Tenstorrent is building RISC-V-based AI processors. They leverage TSMC's 6nm node for their black hole chips, but are also engaging with Samsung and Rapidus for future 2nm designs. This highlights how the foundry model allows startups to shop for the best deal on physics. Grok. Focused on deterministic latency for inference, Grok's Language Processing Unit, or LPU, relies on massive amounts of on-chip SRAM. While their initial generations used GlobalFoundries 14nm, their roadmap involves moving to Samsung 4nm to achieve the density required for larger models. This competitive dynamic keeps TSMC sharp, as startups are price-sensitive and willing to test alternative foundries. Sentient. This company focuses on always-on voice AI, example wake words like Alexa, at microwatt power levels. By using TSMC's ultra-low power, or ULP, nodes and partnering with memory vendors within the OIP, Sentient brought a compute-in-memory architecture to market that enables AI on battery-powered devices. Halo. An Israeli startup delivering high-efficiency AI for edge devices, cameras, cars. Halo leverages Avanet ASIC, a TSMC VCA, to manage its manufacturing. This relationship allows Halo to produce sophisticated 26 TOPS chips without needing the internal operation scale of a major semiconductor firm. Advanced packaging, the new Moore's Law. As the physical scaling of 2D transistors slowed, TSMC pivoted to advanced packaging as the primary vector for performance scaling. This domain, branded as 3D Fabric, has become the bottleneck and the enabler of the AI supercycle. Chip on wafer on substrate, CoWoS, was developed by TSMC in 2011. Initially, it was a niche, expensive technology used primarily by Xilinx for FPGAs. However, the physics of AI demanded it. The memory wall. AI models are memory-bound. They need high-bandwidth memory, HBM, located as close to the logic processor as possible. The interposer. CoWoS places the GPU, logic, and the HBM stacks side by side on a silicon interposer. This interposer provides thousands of microscopic wires that connect the two, offering bandwidths terabytes per second that a standard circuit board could never achieve. Current status. Today, nearly every leading AI accelerator, NVIDIA H100, Blackwell, AMD MI300, Google TPU, relies on TSMC's CoWoS capacity. The technology has evolved into variants. CoWoS S, Silicon Interposer, highest performance. CoWoS R, Organic Interposer, cost optimized. CoWoS L, uses local silicon bridges to connect dies, allowing for packages larger than the reticle limit, supercarrier. System on Integrated Chips, SOIC, represents the next frontier, true 3D stacking of die-on-die without bumps using hybrid bonding. Mechanism: 2 sheets of silicon are bonded directly, copper to copper. This allows for interconnects that are incredibly dense and short. Application: AMD uses this in its V-cache processors, stacking extra cache on top of the CPU, and MI300, stacking logic on I/O. This technology allows chip architects to fold a chip in half, placing memory directly on top of compute, radically reducing the energy cost of moving data. The geopolitics of the Grand Alliance. In the post-2020 era, the democratization of design has intersected with the hard realities of geopolitics. TSMC's role has shifted from a purely commercial vendor to a strategic pivot point for the global economy. Taiwan's dominance in advanced manufacturing, producing 90% of the world's most advanced chips, is often referred to as a silicon shield. However, the concentration of capacity has created anxiety among Western nations. Arizona Fab 21, in response to customer demand and U.S. government incentives, the CHIPS Act, TSMC is building a massive complex in Phoenix, Arizona. This fab will bring 4N and 3N production to U.S. soil. Strategic impact. This expansion is critical for U.S.-based customers like Apple, NVIDIA, and AMD, as well as defense contractors and startups like Tensor Torrent, who require a secure domestic supply chain for their most sensitive designs. It ensures that the democratization of design is not threatened by geopolitical instability in the Taiwan Strait. Competitors like Intel Foundry Services, and Samsung are aggressively trying to build their own foundry ecosystems to challenge TSMC. However, the Grand Alliance creates a formidable moat. IP lock-in. If a startup designs a chip using TSMC-certified IP, for example, an ARM core hardened for the N5 node, moving to Intel's 18A process requires redesigning and revalidating that IP. This creates massive stickiness. Ecosystem inertia. The collective R&D of the Grand Alliance means that EDA tools are often optimized for TSMC first. When Synopsys releases a new AI-powered routing feature, it is often trained on TSMC data. This time-to-market advantage is virtually insurmountable for a startup burning venture capital, reinforcing TSMC's position as the default launchpad for innovation. From 2000 to 2024, TSMC transformed from a capacity provider into the bedrock of the global technology economy. By solving the crisis of complexity in the mid-2000s with the Open Innovation Platform, TSMC enabled a virtual IDM model that allowed disparate companies to cooperate as if they were a single vertically integrated giant. Through value chain aggregators, TSMC democratized access to silicon, allowing a garage startup to access the same atomic-level engineering as Apple. Through advanced packaging, INFO and CoWoS, TSMC extended the performance curve beyond the limits of lithography, enabling the smartphone form factor and the generative AI explosion. The silent hand of TSMC is visible in every major tech wave of the 21st century. It facilitated the mobile internet by partnering with Apple and ARM, it sustained the crypto experiment by supporting Bitmain, and it is now powering the AI revolution by manufacturing the brains of the hyperscalers and the challengers alike. As the industry moves toward the Angstrom era, A16, A14, the symbiotic relationship between TSMC's manufacturing prowess and the world's distributed creativity remains the primary engine of human technological progress. The fabless revolution did not just survive the complexity crisis. Thanks to the virtual IDM, it conquered the world.